In 2011, teaching a computer to see was an incredibly rigid process. Engineers relied on a highly manual method called handcrafted feature engineering. If you wanted a machine to recognize a car or a pedestrian, a human programmer literally had to write out the mathematical rules for every single shape, edge, and shadow the camera might encounter. Think about a stop sign. You can easily code a mathematical rule to look for a red octagon. But when a winter storm covers half of that octagon in white snow, the rule breaks and the machine fails to recognize the object. Now multiply that single point of failure by every variable on the road: nighttime darkness, sudden lens glare, a dented bumper, or a pedestrian stepping out from behind a parked truck. Navigating a highway in a torrential downpour means processing a chaotic, overlapping mess of high-density visual data every second to keep occupants safe. Trying to anticipate every environmental edge case with human-written logic reached a point of diminishing returns. This rule-based approach kept computer vision confined to the lab, struggling to handle the visual chaos required for mass-market autonomy. That bottleneck on machine intelligence held until September 2012 at an academic computer vision competition called the ImageNet Large-Scale Visual Recognition Challenge. A team of 3 researchers, Krizhevsky, Ilya Sutskever, and Geoffrey Hinton, submitted a deep convolutional neural network. It was a multi-layered algorithm they called AlexNet. This chart shows the 2012 competition error rates. The runner-up struggled with 26.2%. AlexNet reached an unprecedented 15.3%. In a field where progress was measured in fractions of a percent over years, an instant 11-point gap was a staggering statistical anomaly. That single margin of victory abruptly settled a decades-long academic debate. It proved that deep learning algorithms actually worked for complex, real-world applications. The success of AlexNet was a structural engineering triumph, the result of 3 separate streams of technology converging at the exact right moment. The first was architecture. Geoffrey Hinton's team had spent years refining theories on deep neural networks, mathematical structures that most of the scientific community had largely ignored. The second was raw material. The architecture finally had enough information to learn from, thanks to ImageNet's massive database of 1.2 million carefully labeled photographs. And the third was horsepower. The team took NVIDIA processors designed for video games and repurposed that raw computing power to run their algorithm. Together, these 3 factors created a new reality. Instead of human engineers struggling to define what an algorithm should look for, the system could now ingest vast amounts of data and learn what to look for on its own. Moving from hand-coded engineering to data-driven learning was the mechanism required for machines to interpret the physical world with enough reliability for the automotive industry. The academic shockwaves hit the boardrooms of Detroit and Stuttgart almost immediately. Within 36 months of the ImageNet competition, every major automotive manufacturer and Tier 1 supplier had pivoted their research entirely toward deep learning. It rewired the factory floor first. Manufacturers began stripping away the old bottleneck of human visual checking for quality control. In its place, they installed automated, AI-powered camera systems capable of scanning production lines and detecting microscopic defects that a human eye would never catch. Then, the technology moved out onto the street. This same computational foundation allowed camera-based advanced driver assistance systems, or ADAS, to transition from niche high-end options to standard equipment on millions of consumer vehicles. Massive corporate realignments followed the data. NVIDIA pivoted its focus from gaming hardware to building autonomous vehicle computing platforms, while companies like Mobileye turned this camera-based intelligence into a global industry standard. Deep learning turned computer vision from a research curiosity into an industrial capability. But as the industry raced forward, they were about to discover the friction of integrating this new software intelligence into century-old metal hardware architectures.